Hope everyone had a good weekend. Before I get into the lecture today, I wanted to do a couple of clarifications of things I talked about earlier. First up is how the assignment 1, question 4, like the coding thing, should be run. The assignment outline says that it'll be ran with the command like of the form java your file name a1q4test.txt. And last term, that misled a lot of students into thinking that it will only ever be tested with that command, when in reality, it'll be tested with all of the files in the test files directory, except for expected output. So I'll just do another quick demo of what running the assignment should look like. This also serves as a reminder of the fact that we're using the command line for this. So type cd stands for change directory. Directory is an old word for folder. That's what they were called before they made up the visual metaphor of a folder. And then drag the folder into the terminal to sort of automatically type it. Something similar probably exists on Windows and most Linux distributions. Actually, I didn't mean to go into the test files directory. I meant to go into assignment 1. So I could fix this by doing cd and then dragging assignment 1 into there. But I'm going to use the command line to do that. I change directory, and then ... is like a shortcut for the folder that contains this one. This isn't like mandatory knowledge for the course. It won't appear on any test ever. But the markers are going to use the command line to test your coding assignments. So this is useful to know. Anyway, Java, my name, okay, and then the assignment outline said that it would be tested with a1q4test.txt. That works. But it should also work if you use anything else. I just pressed tab to show potential completions of this command. So let's try, I don't know, large test 1. Also works. Prints different numbers. Might have even noticed it took an extra second there. So that's all to say. Lots of students last year lost a lot of marks because their programs only worked with the first test file. So don't do that. One more clarification before we get onto this lecture. A student pointed out after the previous lecture that this expression with summations isn't quite set up so that we could use the summation identities we learned about. Namely, this summation has its loop variable starting at 0, but it has a variable inside of the expression. So by the stuff we've learned so far, you would think that we need to do some reindexing or like adding and subtracting, canceling out shenanigans to make this work. But this slide just uses another summation identity. Ignoring the 3, the thing in the first square equals the thing in the second square. And if you use this summation identity on an assignment, the marker will know what you're talking about. So this might be a helpful trick if you're ever dealing with summations that start with 0 but have variables in them on an assignment. All right, let's get into some stuff. First up, we have a sort of warm-up based on the previous lecture. There's nothing new here, but it's worth going over before we get into new stuff, because our new stuff is going to build on this. we want to compute a cost function for this program. And so we count steps as before. Remember that one step is one line that only contains primitive operations. So this line's one step, this line's one step. We're going to worry about this later. This line's one step, and this line's one step. So f of n is going to look something like this. Yeah, that's our template. We have one step from line 1, step from line 2, some sort of summation. We'll figure that out in a moment. And then one step from line 4 and one step from line 5 inside of the loop. Before we figure out how many iterations the loop goes through, we can apply what we know is true for all loops, namely that checking the loop condition will constitute one more step, and that you have to check the loop condition once more so that you know to terminate the loop. So let's finally get to the best part of this, the summation bounds. So we see that we're using a variable k that's counting up by 3 each time, or each iteration, and it starts at 1. So like before, we don't really have the tools to express the fact that k goes up by 3 every iteration. So we work around this by just changing the summation bounds. In previous examples, we've messed with the loop variable that the summation was already using. So like we'd start with k and then write like k divided by 3 or something. But what might be a more elegant method is to just define a new loop variable. So we're going to let j equal k minus 1 over 3. That division by 3 is to account for the fact that it increases by 3 instead of 1 every iteration. The minus 1, the purpose of that is a bit more subtle, but it is a convenience that makes it so every value that j takes on is going to be a multiple of 3. It's just going to be nicer to work with 0, 3, 6, 9 than 1, 4, 5, 6, 7, 10. So j starts at 0. And goes up to n divided by 3 plus 1. And then we'll add up all those ones, evaluate the summation identity. And then we can use the summation identity for constants to simplify it. Since we're going to end up with something along the lines of n divided by 3, and then we're going to multiply by 3, those things cancel out. We just get 3 plus n. It's nice.
Right, sorry. So if, for example, if k started at 4 or something, then would we say k minus 4 up there would be like k minus 1 divided by 3?
Yeah, definitely. The same principle would apply. It would be much more clunky to deal with loop variable values like 4, 7, 10, and so on than it would be to deal with 0, 3, 6, 9, because you want them to be multiples of 3 for this to elegantly work out. Of course, if it started at 6, what I'm talking about wouldn't apply. You might still want to subtract 6 from that in order to sort of make it look the way it usually does. mostly aesthetics. So yeah, 3 plus n. Now for something new. We're going to talk about if statements. So suppose a program contains an if block, and let's attempt to count the number of steps this takes. So line 1, that takes 1 step. Line 2, well, yeah, I think this takes 1 step as well, because you're always going to sort of evaluate the expression inside of the if statement. So yeah, that takes 1 step. And then line 3, well, in isolation, it takes 1 step, but we don't actually know whether this is going to execute. So like, do we take a statistician's approach and say that it takes half a step because it might take 1, might take 0? Do we ignore it because we don't know? Do we say that it takes 1 step because obviously it takes 1 step on its own? All of those are okay answers. One of those answers was the best one. So there are basically 3 different ways you could handle if statements while analyzing code. The best case is to count the smallest possible number of steps. So like, what's the fastest way this algorithm can execute? In this case, if the condition on line 2 is false, if A is odd. The worst case counts the largest possible number of steps. In this case, if the if statement evaluates to true. And then average case averages the number of steps over all possible inputs. So over all possible values of A, we know that half of all integers are even, the other half are odd. I don't know if that's a mathematically valid statement given shenanigans with countable infinities, but it's intuitively true. If you just get an integer, you have no idea what it is, you could say that it has a 1/2 chance of being even. So if A is either even or odd with probability 1/2, you could compute the number of steps as an expected value. It has 50% chance of taking 2 steps, 50% chance of taking 3 steps. So on average, it'll take 2.5 steps. That's cool, I guess. But you can imagine this getting really messy with programs that have multiple if statements, programs that have nested if statements, and worst of all, programs that have inputs that aren't just one of 2 possibilities, both with probability 1/2. In the real world, some inputs are going to be more likely than others, and you could probably waste a lot of money on a consultant who will take 3 months to do a research project and then tell you that all inputs have probability 1/2 or something. This often isn't very practical. In the real world, the most common analysis, actually in the real world, it's actually a pretty tough competition between worst case and average case. In more advanced theory, the most common type of analysis is worst case, because it provides an upper bound on the resources that the program will use. You could think of this resource management in terms of some other task that, such that you don't know how much resources it'll take. Like, if you're driving to school and buying exactly as much gas as you think you'll need to make that one drive, it would be way smarter to plan for as if you're going to hit every red light than to plan for as if you're going to hit every green light. Taking the worst case analysis guarantees that your prediction of how much resources you'll need, in this case fuel, will be enough to do the task, in this case, drive to school. Similar idea applies for computers. If you're trying to figure out how much time something will take, and you're doing some sort of real-time application, like maybe you're programming for a pacemaker and your code absolutely cannot take more time than it's supposed to, literal life or death situation, you check the worst case scenario so you can plan accordingly and know that you'll always have enough time. Okay. So in this example, we have an array of integers a, and the program below finds the sum of the even entries in a. We're going to find the worst case cost of this algorithm. So it's nice to start off just at the beginning of the program, especially since we don't have any nested loops. We won't have to apply any of the stuff from last class yet. So this is one step, one step, one step. That's a loop. We'll deal with that later. And then on line 5, well, that's one step to check the if statement. We're going to assume that the if statement always evaluates to true. So that line 6 takes one step, and line 7 takes one step. Cool. I hope that's the right number of ones. Any off by one errors will be corrected in the following slides, I guess.
Is the fourth one like for the condition? Summation?
This one?
No, the inside the summation.
This one?
Yeah.
Probably. So we've got 1, 2, 3 lines in the loop, and yes, that one is how it has to check that k is less than n every iteration. So under the assumption that we have the worst case runtime, our analysis is pretty similar to what we've done before, but it has another step of clarifying what exactly the worst case is. So what should I do first? The slides do the worst case analysis first, so I'm going to do that too. So if we're analyzing the algorithm formally, we can't just say, let every if statement evaluate to true. Some if statements can be mutually exclusive. You could logic yourself into an impossible situation if you say stuff like that. So we need to clearly state what conditions on the input, make it so the algorithm takes as much time as possible. So this is if a k modulo 2 is equal to 0, and then check this out, for all k. So that's simple enough. Luckily, the if statement only had one variable in it, being k, but you could imagine the statements like these getting a lot more complicated as we go on. So this is an okay way of saying it. You might get full marks for this, but you could imagine the marker being like a character in a movie talking to a nerd in a movie. The nerd gives an explanation. It's super nerdy. And the other character says, "English, please." So let's do that. So hopefully you recognize this from previous exercises you've done in other classes. The remainder of a number divided by 2 being 0 is a nice way to say that it's even. It's how you're not allowed to say it on the first question of the assignment. So we could say AK is even for all K. Better. We can get even less nerdy though. Every element of A is even. So that last one is what you'd say in an explanation of the worst case. That's what you would put on top of a proof of this algorithm having a specific cost function. Now I wonder if I should do the rest of the algebra, because this is unfinished, but it's all covering stuff that we know about already. I think I'm going to do like a quick gloss over, not use any more space than this, just so we continue to review how cost functions and summation works, but we don't waste time that could be spent learning new stuff. So we should figure out what the bounds for the summation will be. And mercifully, we see that we have a comparison between 2 numbers, one of which never changes, and the other of which just counts up every iteration. So we can clearly see as well that K starts at 0, and that it counts up to n exclusive. It's important to remember that summations use inclusive bounds. So this is for all K that are less than n but not equal to it. Summations count up to the bound, including that bound. So to translate that, we just say that it counts up to n minus 1 inclusive. And that's all I'm going to do for this summation. I'm sure you all can add 1 plus 1 plus 1 plus 1 yourself, and with a bit more effort, simplify the summation using techniques we've gone through. We end up with a cost function 4n plus 4. Yeah, that looks like it checks out. This is probably right. We got 4. This will turn it into 4n. And then we got plus 4. Okay, time for a more complicated example. This is one in which the condition for the worst case might not be immediately obvious. So let's start out with that worst case. We have one if statement, and it's going to evaluate to true if A at index K is less than A at index J. Okay. I'm pretty sure that if he said something like, for all JK, A at K is less than A at J. If you said something like this, I'm pretty sure that's impossible for all j and k, you would run into a situation where a at some index is both less than and greater than a at some other index. So we're going to have to put some sort of restrictions on j and k based on what the code is doing. So let's take closer looks at our variables. We see that k increments in the inner loop, and j increments in the outer loop. And now what do the values start at? J starts at 0, and then, I think this one's important. K starts at the value j plus 1. So since it is given an initial value that is clearly greater than j, and j never increments until the next until the next time k is set to a value greater than j, we could tell from this code that k is always greater than j. So that's a good start. We're probably avoiding the contradiction that we found earlier. But we're still not quite at the point where we can elegantly state what the worst case is. I have no idea if anything works. Oh no, I can't select just the expression. Oh well, I'm going to erase and rewrite the quantifiers. So we know that k always has to be greater than j, so maybe we could augment our logical expression a bit, saying that if k is greater than j, then this happens. I am almost certainly going to confuse k and j at some point during the lecture because they are both one syllable and they rhyme. So be on the lookout for that and call me out if something doesn't make sense. So I think this is a correct expression of the worst case. If for all k and j in some sensible set, like the set of all natural numbers, if k is greater than j, then a at k will be less than a at j. The if statement will be true. So basically, if the program works as expected from the values given to variables, then the if statement will be true every time. But this isn't very sensible. If you handed this in, the marker probably wouldn't know what you're talking about. So we're going to try to translate this. So maybe I've got to think about this because, again, confusing k and j. But I think an okay translation of this is that every later element of A is less than every earlier element. This is better. It uses words. But if you handed it in, this would still have the vibe of a desperate attempt at getting part marks. But thankfully, this is equivalent to something, or to a statement that's much more sensible. A is sorted in descending order. So the second statement was a bit flimsy. We lost a lot of precision. Later elements and earlier elements weren't precisely defined. But if you say that A is sorted in descending order, the marker will know exactly what you're talking about. The array is something like 5, 4, 3, 2, 1, or 32, 16, 8, 4, 2. So it turns out if A is sorted in descending order, then this if statement will be true every time. Worth noting, although it doesn't actually affect our analysis, is that some values of A are actually assigned to during the algorithm, and that could mess up our assumptions about A. Like maybe you could sort A in mostly descending order somehow, and then make it so the statements inside of the if block make it so the if statement is true later in ways that it wouldn't be earlier. Thankfully, this program isn't that complicated. This algorithm, like this block of code, swaps the values at AK and AJ. And while it might be nice to look over this as an exercise later, it's not too important. You can just trust me that the act of swapping array values at K and J doesn't change the fact that A is sorted in descending order. Actually, it's not quite right to say that it doesn't change, but A will still be in descending order for all, I think, elements after J. And then we're just going to move on from that J. Draw it out yourself if you want it. We don't have time for this. These slides have another explanation of why the swapping doesn't affect the worst case condition. I'm going to skip through that too because it's not very relevant to the overall goal of analyzing algorithms, but trust me, it works. I think I'm going to go through the analysis of the algorithm, once we get over our worries that these 3 lines might change the worst case condition, because we only just learned about nested loops, and I think it would be worth going through another example. And I think I'm going to go through the slides instead of actually drawing out all the algebra, just because I often hand wave through the explanations on the slides, which might not be so helpful for anyone studying the slides later. So maybe this will help out someone who's reading the slides later, gets confused, and checks out a lecture video for an alternative explanation. So all the stuff on this slide is to say that the inner loop has some more interesting summation bounds than we've seen earlier. So k starts at value j plus 1, as seen earlier. And then it counts up to n minus 1. Notice that this inner loop has a number of steps to it that depends on a variable outside of it. In fact, a variable that will be incremented as part of the outer loop. So the inner loop will take a different number of iterations every time that it's ran. We could see this from the code as well. K starts at j plus 1. J is incremented every iteration of the outer loop. So asking how many steps are taken from lines 5 to 10 doesn't have a definitive numerical answer. It depends on j. So we compress those lines. We say that lines 5 to 10 take up a number of steps that depends on both n and j. This is definitely a space for another warning of avoiding past students' mistakes, but I'm not quite sure how to phrase it. A lot of students hand in expressions for their cost functions that aren't in terms of the right variable. So remember that the function is, by convention, going to be in terms of n. N is like the input to the function. Technically, the input to the function is the array A, but we say that it has length n, and then n never changes. Right now, our cost function has a j in it, but that's going to be the loop variable or the loop counter variable for the outer loop, and that should disappear when you're writing the summation, or when you're simplifying the summation. In the end, your cost function should only depend on the input, not anything that happens, or not any variable that's manipulated inside of the program. So it should just have n's in it, not j's. So we analyze the outer loop now. It increments pretty simply, just goes up by ones, starts at 0. We add up the number of steps that take place inside of the loop, and it's like 1 plus 1 plus 1 plus the number of steps that take place in the inner loop. So 1 plus 1 plus 6n minus 6j minus 5 plus 1 gives us an expression. And now this summation expresses the number of steps that take place during the entire outer loop, including the inner loop. It counts using the variable j. and then the j inside of the expression expresses how the inner loop takes a different number of iterations on every iteration of the outer loop. And then we simplify it as before. This is sort of using another secret summation identity. This counts up to n minus 2, and as a result, we get a slightly different expression. You could use this too on assignments if you want. I recommend doing some reindexing stuff. Still used as a secret summation identity with secret in quote marks, but the fact that it counts up to n minus 2 isn't a problem. The weird bit is that it starts at 0. So I would still recommend on assignments to reindex the sum so that the loop variable starts at 1, and then you could use the standard summation identity. Another thing I wanted to point out is that on this term, or this summation, we have the expression 6n minus 2. N is a variable, but it's not the counting variable. N will have the exact same value in all terms of this summation. As such, you kind of have to treat n as a constant because as far as this summation goes, it is constant. The value of 6n minus 2 doesn't change as j changes, so you use the summation identity for constants. And then the rest of this is just kind of mechanical work, stuff where you're probably going to get an off by 1 error, and I'm going to tell the marker to forgive off by 1 errors, but not that many. We add one more step to reflect the final iteration of the outer loop, count the lines that are not inside of any loop, and thus contribute a constant amount of steps. And then we get a cost function. Yay! Notice stuff from way earlier. Okay, so this example has one loop. There is a loop, and that loop contains a constant number of steps. It has an if statement, but as discussed, we're using worst case analysis, so we say that the if block takes a constant amount of steps. So with one loop, we end up with a cost function that is a polynomial of degree 1. The largest exponent of the variable in that polynomial is 1. Now we have a algorithm with a nested loop. There's a loop inside of a loop. And then the cost function that we get, there we go, is a polynomial of degree 2. You might be seeing a pattern here. If we had, ignore all the content of this slide for now. I'm just using this for extra drawing space. If we had an algorithm that had 3 loops all inside of each other, then its cost function would be a polynomial of degree 3. So you could see that as the number of nested loops grows, the degree of the polynomial of the cost function increases. And that translates to pretty huge runtime growth. Hesitant to say this very confidently, but I think you could say that the runtime grows exponentially as the number of nested loops increases. Don't quote me on that, though. At the very least, I could say that the runtime grows quite a bit as you add more loops. So keep that thing about the largest exponent in the cost function in mind. That's going to come into play as we look at more advanced theory. And it turns out is part of the little slice of this topic that you'll actually need to remember on a job. Of course, all of this is nice in a workspace because then you'll know exactly what you're talking about. But yeah, I have to admit, only a small part of this is actually discussed at companies daily, and it has something to do with exponents. Okay, what do we have here? I think this is just a more complicated example of both if statements and nested loops. This is quite a bit of code. We see that there's one if and a corresponding else. So previously, we didn't have any else's. And so to find the worst case scenario for the algorithm's execution, we looked at the condition inside of the if statement, and then if that's true, every time that if statement is ran, we have our worst case. So defining the worst case for this algorithm would be really easy. AK equals BK for all K. That's pretty easy to translate into English. This means every element of B and K are the same. Or each element of A is equal to a corresponding element of B. That was harder than I thought. Better way to say this would be A and B are the same array. They're equal. Assuming they have the same length. Phew. Anyway, it's not that simple. If any element of A is not equal to the element at the same index of B, then this else block runs. And that may or may not take as many steps as if the if block ran. So we don't know what the worst case is, and we're going to have to just do some algorithm analysis straight away in order to find out how many steps each block takes, and then we could figure out a worst case. As per the example, we're going to start by assuming that AK equals BK for every K. So the two arrays are equal. Oh yeah, and we're only considering the lines inside of lines 15 to 17. So our first step of our analysis is acknowledging just how if-else statements work. If, oh my gosh, spoilers. Oh yeah, if that if statement evaluates to true, then we could just disregard lines 10 to 17. So that's exactly what we do in step 1. Then we look at the number of steps that are inside of the loop that, or the block that does run. When you're reviewing this on your own, I strongly recommend looking at like these slides while having the code open nearby. So depending on your style, it could be in a nearby window on your computer or on a nearby page on your desk. Also, let me know if you want me to slow down at any point. I'm sort of glossing over the mechanical details of this analysis because we've already covered how to count steps once we know what blocks are going to be evaluated, and also how to handle loops. So I'm not going to go into much detail about those, but if you want me to, put your hand up. Oh. So we find that the number of steps taken in that if-else block, assuming the if condition is true, is 3n plus 3. And we're not, like I mentioned, we're not going to go through the mechanical details of the math, but at a glance, this looks correct. There's a loop where the loop variable starts at 0, increments by 1 every iteration, and then counts up to n. Said loop has 2 steps inside of its body, and 1 step for counting the loop condition. So that's 3n plus 1 step here, and 1 more step to check the if condition on the last iteration of the loop. Oh, right. 1 more step because we're counting the if check. Did I say iteration? I meant 1 more step. Sick. And based on what I talked about earlier, we see that this has 1 loop. We're ignoring this outer loop because we're only considering the steps from lines 5 to 17. But anyway, the if block has 1 loop, so it results in a cost function that is a polynomial of degree 1. That's another sanity check that you could do, just to make sure that you're on the right track with this analysis. Likewise, the else block has 2 loops. Like, I never know how to say this when counting. Maybe you could say 2 nested loops. Nesting of depth 2. I don't know. You see what I see, though. There's a while inside of a while. So we're going to end up with something involving an n squared. I'm just going to leave that there, and then we'll expand on the actual number of steps later. Actually, I'm going to erase it. I'm not going to have enough space to put in a coefficient and put this line. Okay, so next up, we're going to assume that for any given k, AK does not equal BK, and consider lines 15 to 17 again. So This if statement is evaluated once more, and it evaluates to false, so we ignore this much. But crucially, the if statement is still executed, so even though it's quite far away from the code that we're actually looking at, we still have to count it as a step. And actually, I'm going to erase a little bit here. And then hope that this isn't too misleading. Actually, I'm going to write 1 here and decrease that. So while it was true previously that lines 5 to 17 took 3n plus 3 steps when AK was equal to BK, I'm just going to split it up a bit more. 3n plus 2 plus 1. So yeah, lines 6 to 9 are skipped and lines 10 to 17 are executed. This is another convention. We say that line 10 else doesn't contain an operation because that's just like a convenience for the human reading the code, or the human writing the code and the compiler reading the code, to say that this is the place to jump to when the if condition is false. It doesn't actually constitute another step. However, if you disagree with me, and on an assignment you say that else takes 1 step, and then your cost function is 1 step larger than the answer key, you'll lose like at most half a mark, because while your answer would disagree with mine, it disagrees in a way that was well explained and isn't really that important. But when I'm doing this analysis, we're going to say that else's don't contribute any steps, because I said so. Okay. We're going to consider next the inner loop in lines 14 to 16. M starts at 0 and counts up by 1. Notice the references to specific lines. That's something that you should definitely replicate in your assignments. And then we get a number of steps for the inner loop. Notice again that it depends on a number that is sort of outside of that loop. So the number of iterations that the inner loop takes is going to depend on the current iteration of the outer loop. So we compress the inner loop into 1 pretend line. Say that that line takes 3j plus 4 steps instead of just 1. Excuse me. Because the, excuse me again. Because the loop took 3j plus 3 steps, and then we add 1 more step for the if condition becoming false. Next, we're going to consider the outer loop. We see that, j starts at 0, increments by 1, up to an exclusive bound. So its summation is going to be decently simple. We figure out the number of steps inside the loop by just adding up those constant time operations, those steps, with the variable number of steps inside of the outer loop. Inside of the inner loop. Evaluate that sum and use the correct summation identities. And then we get a polynomial of degree 2, all according to plan. So that was the outer loop. Last thing we have to do is add the constant time steps that were outside of any loop, and we get the total number of steps. Okay, so then the slide said 3n squared over 2 plus 11n over 2 plus 3. That count included line 5. So for the sake of splitting things up, we're just going to decrement that. And I'm going to try and make it as obvious as possible that this is a 1 and not just some line. Cool. Sick. So now we know how many steps the region of lines 15 to 17 will take in both possible cases. So for any given k, if ak equals bk or not. So let's use that to calculate the number of steps that this algorithm takes in the worst case, and along the way, figure out what exactly the worst case is. I'm going to try and copy and paste the annotation I made above because it's way more helpful down there than up here. Okay, can I paste? Hello? I undid my action instead of pasting. Good enough. I'll look into this further after class. Okay, so we have that in the if-else block. Then if ak equals bk, we have this polynomial number of steps. And if it doesn't, we have this polynomial number of steps. This opens up a actually really deep discussion about comparing functions. We all know about comparing numbers. We could say that 5 is less than 10. Cool. And there are a lot of cases when you would want to do the same thing for functions. So for this algorithm, in one case, the if-else block takes that many steps. In the other case, takes that many steps. Which number of steps is larger? It depends on a variable, so you can't quite say that one is definitively larger than the other for all possible n. But that won't stop us from trying. We're going to look at more robust ways to tell if one function is greater than the other. But here's a nice technique to start with. We just subtract the functions and notice that the difference between the functions is a function that is positive for all positive n. So let's reduce this to numbers. I'm going to use 5 and 10 again. You get 10 minus 5 equals 5. Wow, that's crazy. Notice that 5 is a positive number. So since the difference between 10 and 5 is positive, we know that 10 is greater than 5. I didn't choose those numbers for any specific reason. The example works for any pair of numbers. If the difference is positive and the first number is greater, If the difference is negative, then the first number is lesser. That actually might be how your computer does greater than and less than comparisons. It's definitely how the LC3 from Comp 2280, Introduction to Computer Systems, does it. That's definitely how it does it, but I'm not sure about like real computers. Anywho, their difference is a positive number, so we know for sure that this function is always greater than this function for all positive n. Recall that this greater function is the one that we got from analyzing the case where AK was not equal to BK. So this means that the worst case occurs if AK is not equal to BK for all K. So all elements of A and B are distinct from the corresponding ones. So that lets us compress lines 15 to 17 really nicely. Our function is now really short. We see that there's a few constant time operations, and then a loop where a variable that starts at 0 counts up to a specific variable exclusive and counts up by 1 every iteration. That should sound pretty familiar. It results in a nice, easy to handle summation. We're really glad that the while loop didn't say anything like K plus equals 3. So inside of our summation is an expression representing the expression for lines 5 to 17 that we found earlier, plus a constant amount of steps for things like checking the loop condition and incrementing the loop variable. So we end up with that. Simplifying the summation gives us this. Notice that it was actually really easy. We just sort of replaced a summation with the variable n multiplied by the expression that was already in the summation. And that is another example of how if there are variables inside of the summation expression that aren't the summation's variable, like the variable that's counting up by 1 as the summation goes on, then you could just count that as a constant. All this stuff depending on n might as well be 3. So we have the number of steps taken over all iterations, add the constant number of steps that are outside of any loop, and we get this. So we're basically at the end of the lecture, but I'm going to keep talking for at most 6 minutes because there's another important clarification for the assignment that I want to make. Before that, check it out. It's a 3, and we had 3 nested loops. It just works. Okay, so for the assignment, I'm going kind of off the book here because this is perplexingly not shown in the course, but was in the assignment last term and the term before when I didn't even teach this course. So I'm going to state this explicitly rather than leaving you to just figure it out. If you call a function, fine, call another method as part of your code, let's say func cool func. You had a second function which took some number of lines or some number of steps. Whatever. I know that I didn't define k. What are you going to do? Take a mark off me? So this function takes some number of steps, probably a function in terms of n. And let's say we called cool func right here. So this imaginary line 4.5 would not take one step, but it would take as many steps as that function takes. Also, be very careful about parameters. I passed k to cool func. So this function's n is different from the outer function's n, and its k is different from the outer function's k. You know all this. You've programmed before, but it can really still trip you up while you're doing this new thing of analyzing the number of steps in a program. So I'm going to erase this because it's going to make zero sense out of context. And just say that on the assignment, you have like the standard deviation algorithm that uses the arithmetic mean algorithm. So when you're analyzing the standard deviation algorithm, make sure to correctly count the steps taken by the arithmetic mean algorithm. Okay, that's all the content and all the disclaimers. Let me know if you have any questions, and I'll see you tomorrow.